Okay, let's continue with our model-based approach. So we've chosen two features, yeah? And again, the number of features you choose is a hyperparameter which you tune during cross-validation. This is a normal course of business for machine learning. So the features romance and thriller, which I put next to the users, and I also put next to all the movies. Now, to solve this problem and to fill in the blanks here, there's two ways. One way is gradient descent, and we've seen it in the first few lessons when we dealt with regression. Another one is neural networks. We will not go into detail on neural networks because this will be covered in a later chapter. So we'll focus on gradient descent. And what was the issue? Well, remember, we tried to predict the price of a house given its size. Yeah? In order to do that, we looked at houses in the neighborhood of the house that we wanted to know the price for. And these gave these 6 black dots here. Yeah? These are the prices and the sizes of the houses that we found that were sold in the past few weeks. Now we decided that we want to have a linear model. Yeah? That has a consequence. So you as a data scientist, you choose the model that has a consequence. The consequence is that there's no line that goes through these 6 points. So you will need to find the best line. So the fact that we're modeling, we're going to pay a penalty, a price. Yeah? And that price is what we call a cost function. And the cost function in this case was the mean squared error, meaning that what we looked at was the vertical red stripes here, which is the difference between the black points, the true y, and the point on the blue line, which is the predicted y. So the cost that we pay is we're gonna take all these little red verticals, square them, add them up, and divide by the number of samples. And in this case, we had 6 samples. So this is our cost function. And then we said that we want to minimize that cost function. And minimize we do by gradient descent. Basically, you take the derivative of the cost function with respect to all the parameters, and you set this derivative to 0. And this you iterate through an update rule. But let's not complicate it too much. Let's go back to the matrix here. So we have here a rating matrix, which is a 4 by 5 matrix, 4 rows, 5 columns. And this is here the item matrix, and this we call the user matrix, U transpose. You see here we scored, we will try to score the users on these 2 parameters or features, and the same for the movies. So this here, this red rectangular, this is a vector that we will call P of U transpose. Now, because we want the vector to be column, this is a row, so we transpose. Yeah, and then here, this vector for JAWS, this we will call QI. Okay. So let me remember you what the goal is here. We have a matrix R, and we want to write it as a product of 2 more simple matrices, and we want to reduce the number of calculations by choosing these features. Yeah. So U is a vector 4 rows 2 columns. 4 rows, 2 columns, and I is a vector 2 rows, 5 columns. So this is okay. So R is a 4 by 5. So we're good. Okay. Now, the next thing we need to do, we need to define a cost function. So we will define a cost function. And in this case, we will take half of, we will also take the mean squared error. Half of RUI, yeah, in this case is Anna Joss, right, minus PU transpose QI, and this we square. For the same reason we square here, is to penalize outliers and to make sure that this difference is always positive. Yeah? So basically we compare the value in the matrix where the value exists with the dot product of these two little vectors. Yeah? So let us put some values in here and see where we at. Okay? Anna, for example, she scores higher on romance. So let's assume that Anna, with respect to romance, is 0.5. This could be any number. We just try to initialize now. Yeah, we're not trying to make it right from the first time. And then for thriller, I give her 0.1. Now we need to rate Jaws with respect to romance and thriller. I would say romance is a 1 and thriller is a, let's say a 4. Okay? Just arbitrarily. We could put them all to 0, it will still work. Yeah? I just want to show you now how it works. So we're going to calculate this dot product. Yeah? These are two vectors. And we calculate the dot product. So we do 0.5 times 1 plus 0.1 times 4. Yeah? So we do 0.5 times 1 plus 0.1 times 4. And that is the dot product of these two vectors here. And this I compare with RUI, and RUI is this number. Yeah, so with this, RUI is 1. So when I compare these two, this is 0.5 plus 0.4. So this is actually 0.9. So basically the numbers we've chosen here are already pretty close to where we want to be. So okay, this is the first iteration. We end up with 0.9. Now we go to the second iteration after we updated these numbers. Yeah, and to update these numbers we need the update rule. This is a bit of mathematics, yeah, but it does not change this exercise. And this you have to do for the whole matrix. Yeah, so we'll have to do it. For training, you will have 6 items here. 1, 2, 3, 4, 5, 6. These items will allow you to define these matrices with a minimum cost. And once you have these matrices, you just calculate the dot products and you have your matrix completed. So, gradient descent, we have to minimize the cost function. Yeah? So the cost function we have to minimize, so we need to take the derivative with respect to PU and set it to 0. Okay, if we take the derivative, we have 2 times half, and then we have RUI minus PU transpose QI, and then times minus QI. Yeah, because this is a chain rule, I still need to take the derivative here, and derivative with respect to QI is basically the same, RUI minus PU QI transpose times minus PU in this case. Okay? So this here we will call the error UI. This is the error, the difference between the real value and the predicted value. So this here will be minus the error UI times QI. And this will be minus the error UI times PU. Okay, so what is the update rule? So what are the new values of P and Q gonna be? Well, the new value for P will be the old value of P. Yeah, and then minus the learning rate times the derivative. Minus with that minus makes a plus, and then the learning rate times the derivative will be QI. Sorry, it will be EUI times QI. And for QI, we will have QI plus alpha EUI PU. Yeah? This is your update rule. Alpha is hyperparameter. This is the learning rate. And we usually start with a small learning rate and try to go up. Yeah? It's your role as a data scientist to pick that alpha. Okay, so now we have the formula to update these, and in the next iteration, this here will be even closer to 1. But we do all this with all the elements of the matrix. Okay. One other thing. We like to prevent overfitting, so we need to regularize. Yeah. So we will have the regularization factor that your cost is half the sum RUI minus PU transpose QI squared plus lambda PU squared